Hello everyone, and thanks for Dr. Dongwei for kind introduction. And my name is Chen. And today I'm glad to have the opportunity to present my talk titled towards generalizable tumor synthesis. And feel free to interrupt me if you have any questions. And as we all know, for the past few years, we have been the rise of various generative AI techniques that can produce very high quality images and videos. And here are some examples of AI generated images. And when you look at these images, you will find that they are exceptional quality, amazing, in fact. And on the left in the slide, you can see pictures of people and strange things and at first glance, if you don't look closely, you might think they are really real images from the world around us. In addition to this, current AI can also generate very realistic medical images, such as endoscopic images and brain MRI images and skin images and chat CT images. And let's do a quick test. I've collected some real photos and AI-generated images from the interest. And you have maybe 10 seconds to try to tell which one are real and which one are synthetic. Okay, time's up. I have to admit I was lying earlier. Actually, all age images are AI generated. So how many did you get right? Personally, I can't tell the difference between the synthetic image at all. Similar, when addressing the issue of nuclear segmentation, we have both real or synthesized high-quality images. If I present you with a mixture of both, it will be quite challenging for you to distinguish which one are real, which one are synthetic too, right? And however, with careful observation, you might be able to identify the synthetic images from the real ones. And generating 3D data is a lot difficult than 2D images, but recently a video generative model called Sora has become super popular. And the quality of the video it produced have made almost everyone with details that looks like real world physics. And similarly, generative AI is now also great at creating realistic medical images like CT scans, much like the handle the video data. In the field of computer vision, one important application of synthetic data is its use in visual recognition tasks. And currently, the main application of synthetic data in visual recognition tasks can be divided into three areas. And the one is synthetic data for supervised retraining, synthetic data for data augmentation, and the final is synthetic data for addressing class imbalance. And next, I will briefly introduce these three applications. The first one is synthetic data for supervised pre-training. Synthetic data can be used to pre-train models before fine-tuning them on real data. Uh, this approach shown in this slide leverage large amount of synthetic images to help model to learn basic feature and pattern and validate them in several segmentation tasks. And the table shows the semantic segmentation performance of different segmentation models before and after pre-training with synthetic data. And you can see also using synthetic data directly to train the segmentation model, may not perform as well as model trained on real data. But with synthetic data for supervised pre-training and then fine-tuning with real data, it can improve the segmentation model performance. And the blue and the red blocks in the table indicate this difference in performance. And besides pre-training, synthetic data can also be used to mix with real data to boost the amount and the variety of training data. And by creating variants of existing images like different angles, lighting condition, or background, synthetic data can help make a segmentation model more robust and generalizable. And this approach in this slide is great for uh, preventing overfitting and improve overall performance. And these methods have proven to work well across many visual recognition tasks like semantic segmentation, instance segmentation, depth estimation, and pose estimation, and so on. And this method validates that using synthetic data as a form of data augmentation strategy can has been shown to be very effective and leading to substantial performance gain. And the class imbalance occurs when some classes don't have enough data in the training set. And in real-world data collection process, it is difficult to get balanced data for all classes. Usually, we have resampling to fix the class imbalance when training AI model. But this research shows that generating synthetic data can help balance the dataset, giving the model enough examples for every class, especially for the underrepresented class. And the results in this paper show that the synthetic data works better than just resampling strategies. And next, I will introduce the medical image task, cancer diagnosis from CT scans, and analyzing and diagnosing medical images with computer vision is a hot topic right now. One area getting a lot of attention is using CT images to diagnose cancer. Because it is so crucial to our health and well-being. From this slide, you can see that many types of cancer contribute to the global mortality rate. The one with the highest death rate are most linked to abdominal organs like colon, stomach, pancreas, breast, and the liver. And this shows just how common and deadly these cancers are, and it highlights the urgent need for more focused cancer research. And it's important to improve the diagnosis rate for the cancer. So when it comes to cancer research, there are three main challenges. The first one is data scarcity. And the second one is generalizable to different organs. And the third one is generalizable to different demographics. And next, I will introduce in detail and how we use synthetic data in our CPR work to address these three challenges in cancer research. When it comes to public available tumor data, there are two main challenges. The first one is medical images or tumor data contains sensitive patient information, and the strict regulation, such as HIPPA in the United States, limit the sharing medical images without proper consent, ensuring that data is anonymized sufficient to protect patient privacy, while returning its clinical value is challenging and resource intensity. The second one is collecting high quality tumor data, and their corresponding annotation is time consuming. Getting high quality medical images and their responding annotation, such as tumor masks, tumor class, requires significant resources. For example, expert radiologists must review and annotate the CT images, which is time consuming and expensive. And this specialized expertise is not always readily available, especially for rare tumor types. Due to these challenges, the number of tumor data in existing public datasets is significantly smaller compared to natural image recognition datasets. For example, ImageNet dataset contains around 14 million images, where various tumor datasets only have a few hundred samples. And furthermore, generative model often require large amounts of annotated data for training. So how can we figure out the data scarcity problem for training generative model with limited annotated tumor data? We have noticed that tumors within the same class often look pretty similar. For instance, if you check out the slides showing liver tumors, you'll see that the area marked by the white arrow have lower grayscale values compared to surrounding organ tissue. And the tumors share some common characteristics. They are usually small and have a simple texture and have a uniform shape. Because these similarities, we can use generative model to tackle this issue of data scarcity by making advantage of their tendency to overfit small or few samples. Normally, overfitting is something we want to avoid in common vision tasks, but here, it can actually be a good thing. The texture of tumor region doesn't need to be super diverse. We just need the network to generate realistic tumor data. So even with a small and a few tumor samples, we can train the generative model to learn the key characteristics of tumor effectively. And we also have some results to align the observation. And the first one is we can use very few tumor data to train the generative model successfully. For example, we find in our work, the diffusion model only require just one annotated tumor to train the diffusion model and generate synthetic tumor for the subsequent training of the segmentation model. And this contracted the typical experience in common computer vision tasks, which generally require large-scale data for training the diffusion model or generative model. And the results indicate that we can rely on a small number of real tumor to train the generative model successfully. And the second one is we can the time step of diffusion model to generate tumor. We can have very small time step. For example, in the right figure, when the time step is set as 2, and the diffusion model can successfully generate a realistic tumor data. In other words, the simple texture of tumor doesn't need a very large time step to make the generative model to learn the complex texture or other feature. And the second challenge is generalizable to different organ. And the model trained on data from one organ might not work well on data from another organ. Each organ has a difficult structure, and the cancers in difficult organs can look quite difficult. And in traditional tumor segmentation tasks, we often have to train a separate segmentation model for different type of tumors. For instance, if we wanted to segment liver tumor, we need to use image label pairs of liver tumor to train the segmentation network. When we only need to segment a few types of tumor, this paradigm is acceptable. But as the number of tumor types increase, we end up needing to train many segmentation model. For example, one tumor types for one for each type of tumor. And each segmentation requires corresponding tumor data and annotations, making the entire process very costly and time-consuming. This means that a good segmentation model needs to generalize across various types of cancer. To reduce the workload brought by the current paradigm or previous paradigm one, we aim to use synthetic data to achieve generalizable tumor segmentation across different organs, creating what we call paradigm 2. For example, we can train a segmentation model using liver tumor data, and also the model is trained on one type of tumor. It can generalize to generate other types of tumor in the inference stage of generative model. This way, we can use the generative model to create various types of tumor data needed to train corresponding segmentation networks. So, how can we achieve this goal? And we think the key is find the connection across different types tumor in different organs. And we discovered that early stage tumor tend to present similar imaging characteristics in CT scans. As shown in this slide, the cropped tumor regions from different organs based on tumor masks display a high degree of similarity. To validate this observation, we conducted several experiments from both a real study and feature analysis perspective. The objective of the study is to assess the ability of radiologists to recognize the organ class of early cancer. And we uniform crop 366 images of the tumor region from 3 abdominal organs as per the annotation, and like the last slide show. In order to include the influence of surrounding organ texture on recognition, we only retain a small amount of organ texture in the tumor boundary region. And as we can see the results in these slides, and 3 radiologists quantify under the quality standard participating in the read study. And the final results show that the nearly random probability of the precision and recall scores indicate that the appearance of early stage tumor is so similar that even experienced radiologists have difficulty distinguishing the organ types of these tumors.
Excuse me, I have a question here. I was wondering if the radiologist is looking in a ROI patch or is looking at more global kind of CT scans. It's looking into local globals. Oh, okay.
Qi, can you show the previous slides? Oh, yeah, this is what they're looking at.
So this is not global, it's not a complete.
Because if it's a global,
Well,
if it's global, that's too easy. You can see the organ.
oh, I see. Right, in this case.
Right, you don't want the radiologist to see the organ area and ask them to tell which organ it's cropped from. That's why it have to be local.
Yes, that makes sense, but for the, what about the late stage tumors?
They look very different.
I mean, if you look into the late stage tumor, the radiologist can also not distinguish that because it's local patch.
Well, I'm not sure.
Oh yeah,
I mean, I guess well, no, I mean, let's put it this way, I don't know if they've tested on that, but a radiologist can say whether it's a PDAC or a PNET, for example.
You mean that radiologist can directly looking into kind of local patch and distinguish if it's a PDAC or PNET?
Well, actually, I'm saying I don't know because they're probably never asked to do that. On the other hand, I guess what I'm talking is slightly different here because here the issue is, do you know the organ? And if you know the organ, it can make a difference.
Oh, I know, yeah.
But in the other thing, I was arguing that I think if they're distinguishing between different types of organ and the same thing, they could do it if it's big enough. And that probably doesn't mean that they know what organ they're looking, they know what organ they're looking at, but it probably doesn't help them for that particular task.
Yes.
If you see what I mean.
Yeah, but I'm asking kind of different questions because the standing point that the early stage tumor share similar imaging characteristics, and you're trying to prove these points by kind of a SVM classifier or examined by the radiologist. And on the other hand, it seems that to deliver the late stage tumor has different imaging characteristics. But I think if we have a kind of the similar control experiments, that is, we're asking several radiologists to look into late stage tumors, and I believe they also cannot tell.
Yeah. Yeah, you should. Because this task is not a radiologist's everyday task. It's very difficult. So we choose the early stage just because the texture is simple. and the diffusion model can model this.
Oh.
The later stage, we also try to learn, but the texture is too difficult. So at the moment, the diffusion model cannot make realistic advanced stage tumor, especially if the subtype is not able to generate that.
Oh,
That's why this study will only focus on small stage, the early stage.
oh, I see.
And I mean, the early stage is also what you care about
Oh, yeah.
in terms of
Yeah,
detecting.
and another point is advanced stage, we have a lot of example already in the public data. So, and the model already can tell
Oh,
really miss that. So here the really challenging point is early stage.
Right.
it makes sense.
But I want to pick up a point which came up from Janan's talk, which, as we've discussed, it would be nice to be able to distinguish between different types of tumors in the same organ.
That will be middle or advanced stage, because at the beginning, they are like this. So even Xiaoxi last meeting, she cannot tell the early stage of PDAC and
Early stage meaning what size?
less than 220 millimeter.
You sure? That's pretty big.
I mean, it is classified as the advanced stage. It is classified as small tumor.
That's some medical standard handbook, say early stage.
Oh, well, right. But yeah, just in terms of what we're doing, because I know, and sorry, this is a bit off topic for the talk. Well, it relates to what we can do with the use of synthetic tumors, but in the current algorithms, we are confusing PDACs with PNETs and things. Did you study how that depended on size?
Oh, I mean, for our test sets, they are only kind of 60. And there's just a few PDSC smaller than 2 centimeters.
Oh,
And they are 200 smaller than 2 centimeters.
right. But still, the question is, if your algorithm is confusing them, is it confusing them? Like if they're bigger than 2 centimeters, does it have no confusion at all? Or does the fusion only happen when they're less than 2 centimeters? Or does the confusion only happen when they're less than
Yes,
1 centimeter?
it's a good point.
We don't know. We could check it.
Yeah,
We don't know. Yeah, it's a good point.
Because I'm not. I mean, let's see. First, the reason I'm mentioning it is, I think, as we've discussed. Sorry, Keir, this is sort of slightly independent of the talk, but we've discussed it would be good if we find tumors. We want to say whether they're good ones. Here in the talk, we've just sort of said all tumors are roughly the same. Even more, we've said they're roughly the same in all organs. And I guess I was wondering to know about whether that, how really accurate that is. And also, is that partly that's a finding based on radiologists, I guess. So we don't know if it's a real finding. I mean, so it's a finding on radiologists. They're trained to do different things. And my understanding is often they specialize to find tumors in one particular organ. They don't specialize to find them in other organs necessarily. Elliot's an expert on the on the pancreas, not so much on other areas. Right, so they're specialized in those. They are, right. And so I'm wondering if actually the tumors are actually different and whether AI can pick up on that. Because really, if we run these, because it seems to me, once you get to really small scale, yeah, they've got to be similar, but the cysts are supposed to sort of roughly have bits of liquid inside. The PDACs certainly don't. There must be a certain stage at which they start becoming visually distinctive. But that may not be the stage that the radiologists can distinguish them, because the radiologists aren't necessarily geared to do that. So Anyway, so let's see, what are we on here? Is it okay? Yeah, it's good for these things to be similar so that we can train with data that is different, but we also be trying to get synthetic, see if we can get synthetic that differs on the type of tumors, which I guess we can do on the pancreas because we've got certain annotations. And on these other data sets, we don't. Is that right? We just say there's tumor or...
For the kidney data set, they also annotated the kidney tumor and the kidney cyst. So at least the two subtype we can look into.
Right. Okay.
For pancreas, we have our data sets. That's good.
Okay. But then I think one thing to do is someone check to see whether when you're confusing the tumors on the pancreas, how does it depend on size, which I guess we never checked. We should have done, I guess.
Yeah, and also here the study is totally based on public data where their tumor type is very simple.
Oh, yeah.
Yeah, for liver it's only one type of liver tumor, and for pancreas mostly PDAC.
Right.
They don't have many diverse subtype.
Yeah.
Yeah, so this study have some limitation. We might revisit at some point.
Well, no, I mean, it's an impressive result. I mean, it was one of the results I didn't believe when you first mentioned it.
Yeah.
I mean, because it's so nice that you can switch the tumors. You only have to have them in one organ, and then you've got it from the others. But I am wondering whether, we're focusing on synthetic on sort of slightly crude tasks, which are the ones to start on, and I'm wondering how far we can push it to. Okay, sorry, sorry for that long version. Could we carry on, please?
Okay. And besides read study, we also analyze the similarity through the omics feature of early stage tumor. And quantitatively, we train 3 types of learning-based classifier, including SVM, random forest, and edibles. Although in this slide, we only show the result of SVM, but the result of the 3 classifier is similar. So to draw a general conclusion, we conducted 10 repeated experiments and calculated the precision and the recall scores of these 3 classifiers in both Chen and test set. And the final results for SVM show that the precision and the recall for training set are close to 1. And this indicates that SVM classifier is well trained and capable of learning descent decision boundary for the training set. However, the precision score for the test set are nearly equivalent to random probability, like 33. Similarly, the other two classifier, random forest and edibles, also achieve the similar results. And this suggests that even a well-trained classifier still struggle to recognize the own types of unseen early stage tumor. And in addition, we also showed the TSNE visualization results in a 2-dimensional space, and the appearance features of early stage tumor are distributed in a joint feature space, showing no separation boundary for different organ types. And additionally, we further explain this distribution based on medical knowledge, as shown in these slides. And in summary, we validated the similarity of tumors across different organs. Leveraging these characteristics, we achieve a cross-tumor synthesis, which in turn enable cross-organ tumor segmentation. And in order to verify the effectiveness of our method's generalization capability across different organs, we conducted comparative experiments across 3 different abdominal organs. And this involved training or segmentation on models on tumor data from a single organ. For example, the source data is the training data, like liver, pancreas, kidney, and we evaluate the results, these 3 models on different target organs, for example, liver, pancreas, kidney, respectively. And for the result of our model, we train our diffusion model on source organ data and then utilize healthy CT volumes to synthesize tumors in the target organ. And these synthetic data are used for further training the segmentation model. And to showcase the broader application of our synthetic data, we compare the early stage tumor detection performance across 3 common yields backbones. Also, in this slide, we only show the results of backbone UNAS. And the generalization results suggest that it's difficult to segmentation trained on real data to generalize across different organs, leading to poor performance in early stage tumor detection. And Qixin's work published in CPR 2023 also achieved suboptimal results in this setting. So, in conclusion, the generalization ability with the synthetic generated by our models can achieve generalizable to different organs. And the second challenge in cancer research is generalizable to different demographics. And there are many countless hospitals around the world, and the CT image taken at different hospitals in various regions can vary a lot due to difference in the local population, like age, gender, and other factors. This results in a significant domain gap between the data from different hospitals. And the cancer can manifest differently in various demographic groups, including variation based on age, gender, and genetic background, and so on. If a segmentation model is trained using data from only one hospital, it's likely perform poorly on data from other hospitals. So we hope that segmentation model need to train on diverse data sets that reflect the demographic differences to ensure they work well for all populations. And these challenges highlight the need for more comprehensive data sets and advanced techniques to improve the generalization and the robustness of cancer model for different demographics. And the domain gap between tumor data from different hospital is primarily due to differences in organ. Because the difference, the difference in the different texture in different tumor data across different populations can be significant. To address this, we use an implanting approach that focuses on that make the generative model focus on learning the tumor region only, and this reduces the complexity and the difficulty of training and generating the target or new tumor data. So we use masked and masked volume as a condition to perform the denoising process in diffusion model. Once the segmentation or once the generative model is trained, we can utilize it to generate tumor data for different hospital and population by collecting unlabeled CT scans from these diverse sources with different demographics. This process allows us to create synthetic tumors that reflect the specific characteristic of various demographic group and different hospital. So we also evaluate the results of generalizable to across demographics by using the private dataset JHU. And to perform the enhancement of our synthetic data for segmentation model to detect and segment a real tumor across different individuals, we compute the matrix of tumor-wise sensitivity and the segmentation matrix dice. And due to time limitation, we only show the tumor-wise sensitivity in this slides. And you can see our synthetic data can yield an average improvement of 60.4% in sensitivity with UNAT backbone. In particularly for people aged 50 to 60, the improvement is most significant. For both male and female, there are noticeable performance improvements for tumor-wise detection. So these results demonstrate that our synthetic data can provide valuable assistance in clinical tumor analysis for individuals across various age group and genders. So,
there's quite, sorry, slightly irrelevant.
Okay.
There seems to be quite a big sex difference there.
I didn't get it.
Oh, sorry, there seems to be quite a big difference between male and female. I mean, not in terms of your results, but in terms of the relative results. Was that?
You mean the male scan, the tumor is a segment better?
Yeah, it looks like that by a large margin.
Maybe the male has a bigger organ, more visible.
I just want to check. I mean, no. I mean,
I guess it depends on the healthy CT we use to train the segmentation model. Maybe the healthy CT have more the male CT scans, and so we can generate more tumor data of male gender. So it can bring more improvement on the male people.
well, I'm not so much talking of the improvement on the male. It's just it's just the male versus female. Either your method, your improvement or the original improvement seems quite big. And I thought that what I was always told was it wasn't a huge difference. That's what Elliot would say. I mean, I mean, it may depend a bit on possibly there's some sort of biases in the data set in terms of the size of the tumors in terms of balance, but I guess this actually looks pretty big. This looks pretty big to me. I mean, yes, female 51.4%, male 62.3%. That's 10%, and it still says 10% when you improve it. Maybe look into that. I mean,
Okay.
it's
Yeah, we will evaluate it again. So this is subset of Felix data due to the time limitation, but we will.
look at the size. Maybe, you know, my guess initially is that maybe there was some bias in the size selection here, but maybe this is right, and maybe.
Yeah, we will evaluate all the scans in the benchmark paper. So that one will be include more test set. Then we will see the overall performance between male and female.
Yeah, I mean, the organ size may be slightly on average size, but I don't think with the tumors. Yeah, it's worth looking into. I mean, it's not bad.
Okay.
Okay.
Yeah, okay.
Okay, I'll move on. And so in final, we will summarize our methods. This method involves 3 stages. At the first stage, we trained an autoencoder model consisting an encoder and a decoder to learn a comprehensive latent feature. And the learning task here is image reconstruction, perform a 9262 unlabeled 3-dimension CT volume. So both the Chen encoder and decoder will be used in subsequent stage. And the second stage is that training a diffusion model using latent feature and tumor mask as condition. And once trained, this model can generate latent features necessary for reconstructing CT volumes with tumor based on arbitrary masks. And the second stage is training a segmentation model using CT volumes of synthetic data and real data, and the synthetic data are reconstructed by the decoder. With a large scale of healthy CT volumes, our method can produce a vast array of synthetic tumors, varying in location, size, shape, texture, and intensity. Therefore, forcing high-performance AI models for tumor detection and segmentation. So next, we will introduce some future thoughts about tumor synthesis. For future work, there are 2 aspects to consider in tumor synthesis based on a diffusion model. And the first one is consider more image modality and more tumor synthesis, more tumor types. For image modalities, there are several tumor types in MRI, X-ray image in public data sets. So we can explore the universal tumor synthesis model across different image modalities. And besides, the tumor investigated in our CPR work belong to solid organs, and tumors in solid organ typically exhibit ellipsoid growth pattern. In contrast, tumor in tubular organs grow on the organ wall, showing significant different growth pattern from those in solid organ. And for the second source is to focus on improving the quality of synthetic data. And the currently methods may generate some unrealistic cases. So further, the generative model design could be explored to enhance the synthesis quality. And the one possible strategy is adding data filter or adding extra control. And the process of generating tumors lack necessary control and fails into populous generation. Actually, most application of synthetic data in medical imaging don't concern with the likelihood of themselves, but rather with downstream objectives such as tumor detection and segmentation. In other words, our ultimate goal is to utilize synthetic tumor to improve the segmentation model, but the optimization goal of the synthesis and segmentation tasks are not aligned. So we aim to use the output or features of segmentation model to guide tumor synthesis and iterative enhance both diffusion model and the segmentation model. And besides, we now have a project, Abdominal X. This project aim to build a large-scale annotated abdominal tumor dataset by supplementing data for existing tumor types and creating extensive data and annotation for numerous other tumor types. So this work, the difference of this work with our CPR work mainly include two aspects. The first one is the Abdominal X project will generate more tumor types. For this aspect, we collaborate with Chinese hospital, and they are willing to provide some examples. For example, a few hundred tumor data with two new types of tumor. So we can train our generative model using the new two types tumor and generate corresponding synthetic data. And the second aspect is we adding data field to ensure the quality of synthetic data. Specifically, we developed a tumor correlator to maintain the high realistic confidence for synthetic tumor. And besides, a team of 4 expert radiologists conducted a visual inspection of the synthetic tumors. So finally, 90% of tumor will be generated by our generative model, and the remain 10% by 10% data is the real tumor data annotated by the medical experts, radiologists. So that's all I have to say about the data towards generalizable data synthesis. And thank you for listening. And now if there are any questions, I would glad to answer them.